Welcome to my channel today. In this video, I'll be teaching you how to reduce matrices to echelon form. Then after that, I'll show you how to solve systems of linear equation by Gaussian elimination. From there, we'll proceed to see how to transform matrices to reduced row echelon form. And then we end the video with solving system of linear equations by Gauss-Jordan elimination. So first, let's look at how to reduce matrices to echelon form. Welcome to my channel. Let's see how to reduce matrices to echelon form, or how to write a matrix in echelon form. So the first thing that we do is we need to know, when do we say that a matrix is in echelon form? So a given matrix will be said to be in echelon form if it fulfills the following two properties. The first property is that the first non-zero entry in each non-zero row, must be in a column that is to the right of the other leading entries. So if we have the leading entry in row 2, the column that leading entry is in must be to the right of the column of the leading entry in row 1. And the other property is that the rows consisting entirely of zeros must be at the bottom of the matrix. Now, so let's just note that we say that a matrix is in a row echelon form, or somebody may opt just to say that it is in echelon form. So the two mean the same. When we talk of row echelon form and talk of echelon form, row echelon form and echelon form mean the same thing. So we just need to look at a few examples just to ensure that the two properties that we've looked at, property 1 and property 2, are clear to us. Now, these three matrices that we're seeing here are in echelon form. So I just want to use them to illustrate the two properties. This is a non-zero row. So this, the first element in this non-zero row, the first non-zero element, the first non-zero element in this non-zero row is 2. So we call this the leading element in this row, leading element 2. This is also non-zero row, and the first non-zero element is 2. So it's the leading entry in this row. This is another non-zero row, and the first non-zero element in this row is a 1. So we call it the leading 1. So what I mean therefore is that this element, leading element in this row, is in column 2, and this one is in column 1. So this one is to the right of this. And again, you can see that this leading 1 is also to the right of this other leading entries above it. Let's come to this other matrix. This is a non-zero row. The first non-zero element, the leading element, is 1. The first non-zero element in this second row is this. So it's the leading element for this row. And for this other row, it's this. So you can see that this leading element is to the right of this, and this one is to the right of this. And that is what property 1 means, that every leading element must be in a column that is to the right of the other leading elements above it. And what property 1 means is this, that a row that is made of entirely zeros must be at the bottom of the matrix. The leading element in first row is this. The leading element in the second row is this, and you can see it's to the right of this. The leading element in this other row is 1, and it's the right of these other rows. These are the leading elements. And finally, the leading element is 5. And you can see it's to the right. It is to the right of the other leading elements. So that means as we proceed, for us to write a matrix in echelon form, we'll be considering that. That every leading element must be to the right of the leading elements above it. So the question is now, how do we reduce a matrix to echelon form? So to reduce a matrix to echelon form, we perform the following elementary row operations. We can reduce a matrix to echelon form by either interchanging rows or adding a multiple of a row to another row, or by multiplying a row by non-zero constant, or by combining these properties, these operations, combining these operations. So you may combine these operations so as to reduce a matrix to echelon form. So the process of performing the elementary row operations on a matrix is what we call row reduction. So by row reduction, we just mean apply the elementary row operations on a matrix to bring it to echelon form. Bring it to echelon form by performing these elementary row operations. Now, so very interesting is that let's now look at how to reduce a matrix to echelon form by performing the elementary operations. So we look at the first example, and the example is reduce the following matrix to echelon form. So there are two ways you can proceed from this. The first way, you may want to keep this true the way it is, and then use it to create zeros below it. Or the other option is to create a 1 in this position the way I did, and then use this 1 to create zeros below it. And of course, that is all what we'll be doing. To reduce a matrix echelon form, we are interested with this element. Use this element to create zeros below it. This element is in row 1. Now come to row 2 and create the leading one. No, the leading element in a row. Create the leading element in row 2. And once you create the leading element in row 2, create the zeros below it, and so on. That's what we'll be doing. Now, what I did is that I did not want to work with these two because I thought that would be tedious in some way. So for me to simplify my work, what I normally do, I want to ensure that the leading elements in every row are 1s. That is to make my work easier. I want to ensure that the leading element in every row is a 1. Although you may want to work with the element which is already there. For instance, in this case, you may want to work with this 2. But for me, I'm seeing that would be hard. It would be to consume a lot of time. It won't be hard, but it consume a lot of time. So I want to make it a 1. So to make this one 1, there are two ways. The first way is that you may want to subtract row 3 from row 1. And that is not what I did. Of course, when you subtract row 3 from row 1, you would have a 1 here. But what I did was very easy. What I did was I took row 1 and divided by 2 to get the new row 1. And as you proceed, I must tell you that it's always easier and good to always show us your row operations. So like this is my row operation. I'm just saying that to get my new row 1, I took the old row 1 divided by 2. And when you do that, divide this row by 2, you would get 1 a half, and negative 1. So let me just ensure that my operation remains here. Row 1 divided by 2 gives me my new row 1. That's good. Now, so I now have 1 in this position. It's my leading element. I use this leading element to create zeros below it. So to create a 0 in this position, you can see that I need this row 2. I need row 2 minus 3 row 1. And this one will give me the new row 2. And to get the new row 3, I need a 0 in this position. So to get a 0 in this position, I take the current row 3 minus the current row 1. And that gives me the new row 3. So let's do this and see what we get. So I want a 0 in this position. I have already said row 2, which is 3, minus 3 row 1. But row 1 is 1. The element in row 1 is 1. So this gives me 0, and it is 0 you are seeing here. So I come to this other position. I take the element in row 2 is a negative 3. Then subtract 3 row 1. And row 1 is a half. The element there is a half. So when I do this, this is the same as negative 3 minus 3 over 2. And this, the LCM there is 2. The LCM is 2. And so this will be negative 3 minus 3. And this is negative 6. Negative 6, negative 3. And so this is what gives me negative 9 over 2. Then I come to this other one. This one. I have negative 1 there, then minus 3, negative 1. That negative one, this one will give me positive. So what I have is negative 1 plus 3, which is 2. Is the 2 you're seeing there. Okay, let's clear this. Now, so we need also a 0 in this position. We say row 3 minus row 1. So 1 minus 1 gives me 0. Negative 2 minus a half gives me minus 2 and a half, which is negative 5 over 2. And then 3 minus 1. That gives me 4. So we are done with that. So what is very important here is that we have a leading element, and we use this leading element to clear the first column. So now we are done with that. We come to the second row, and I can see the leading element is this. We can use this to create a 0 below it. But what I did, I opted to use 1 here. I thought using a 1 here would be easier. And so that is what I used. So I created a 1 in this position. Created a 1 in that position by multiplying row 2. Multiplying row 2 by the negative of this reciprocal. Negative of that reciprocal. So multiply row 2 by negative 2 over 9. negative 2 over 9. So the whole row 2 multiplied by negative 2 over 9, it will be 1 here, and it will be negative 4 over 9 here. That's what you're seeing. And the other rows remain the way they are. Row 3 remains where it is, row 1 remains where it is. So I have a 1 in this position. It's easier dealing with a 1. But I would have left it. I would have left it the way it is, but that would consume much of time. So now that I have a 1 in this position, I use this 1 to create a 0 below it. How do I create a 0 here? So that means to create a 0 here, I need to take row 3 row 3 plus 5 over 2 of row 2. That will give me the new row 2, the new row 3. So row 1, I just leave it the way it is. I'm only interested with the elements below this leading one. Those are the only elements I'm interested in to make them zeros. And so, whatever thing I'm doing to this element and this, I'm doing the internal rows. So, negative 5 over 2 plus 5 over 2 of 1 gives me the 0 you're seeing there. I do that again for these other elements. 4 plus 5 over 2 of negative 4 over 9. This gives me 4 minus 20 over 18. Or let me just say this because this is 2. Minus 10. Minus 10 over 9. The LCM that would be 9. And this would be 36 minus 10, which gives me 26 over 9. It is the 26 over 9 you're seeing here. So what did I do next? What I did next, I decided since that my leading elements have made them to 1. So I make the last leading element also be 1. You can see that this is my leading element. So I make it 1 by multiplying this by 9 over 26. Multiply by 9 over 26. And multiply by 9 over 26 you get to 1. So this is what I have. That's what I have. So next we look at this other example. So let's now look at this example 2 and reduce it to echelon form. And you now know what we're supposed to do. We are using our leading ones to create zeros below them. So in this matrix, looking at this first row, first column position, the leading element there is 1. Which we call the leading one. So we use it to create zeros below it. So to create a 0 below at this point, we'll just take row 2 plus row 1. And this will give me the new row 2 that I want. And to get a 0 in this position, I'll take row 3 minus 5 of 1. So this will give me the new row 3. And so that is what I'll be doing. So let me take row 2, this position plus that. So negative 1 plus 1 is what gives me 0 in this position. And then negative 3 plus 2 gives me negative 1. And then 1 plus negative 5 gives me negative 4. And now 5 minus 5 times 1 gives me the 0 here. And negative 13 minus 5, negative 3. This will be positive 15. So negative 13 plus 15 gives me 2. Then here, you take this 13 minus 5 multiplied by 1 is 1. And so we have 8. So let me clear that. Make it like this. And that. From the very beginning, I've said that we can use this to be our leading one, but I'm making my work easier by making it positive 1. So to make this one positive 1, I would want row 2 times negative 1. So row 2 times negative 1. This becomes positive 1, this becomes positive 4, and the rest of the rows remain the way they are. I now have created this leading one. I use it to create zeros below it. So to create a 0 in this position, I would want to have row 3 minus 2 row 2. And that gives me the new row 3. So if I multiply this by 2 and subtract from this, I have 0. If I multiply this by 2, this 4 by 2, I have 8. Subtract from this, I have 0. So my matrix is now in echelon form. The matrix is now in echelon form. So I want to take the last example on how to reduce matrices in echelon form. And the example that I'm talking about is this. Just a minute. Let's clear this. So this is the matrix I have. And I want to reduce this matrix to echelon form. Let me just do that. So I have this leading element here. I use it to create the zeros below it. So what I did, I took, to get the new row 2, I took the current row 2 minus 2 row 1. Then to get the new row 3, I need a 0 in this position. So I took the current row 3 minus 3 row 1. Then I need a 0 in this position in row 4. I took just row 4 minus row 1. And then to get a 0 in this position in row 5, I took the current row 5 minus 2 row 1. So these are the row operations I want to carry out to reduce this matrix to echelon form. So let me just take row 2 minus 2 multiplied by row 1. So this minus 2 times 1 gives me 0. 3 minus 2 multiplied by 2 gives me negative 1. 5 minus 2 multiplied by 3 gives me negative 1. And then 1 minus 2 multiplied by this gives me negative 1. Then we have 3 minus 2 multiplied by 2 gives me negative 1. Then finally 3 minus 2 multiplied by 2 gives me negative 1. So I'm done with this row. I now want to carry out this operation. Row 3 minus 3 row 1. So 3 minus 3 times 1 is 0. 7 minus 3 times 2 is 1. 6 minus 3 multiplied by 3 be negative 3. So I did for the entire row and I come up to here. Then let me go to row 4 now. Row 4, I have row 4 minus row 1. So 1 minus 1 is 0. 2 minus 2 will be 0. 3 minus 3 will be 0. 1 minus 1 will be 0. 3 minus 2 will be 1. And then 1 minus 2 will be negative 1. Then I go to row 5. Row 5 minus 2 row 1, because I want a 0 in this position. So 2 minus 2 times 1 gives me 0. 4 minus 2 times 2 gives me 0. 6 minus 2 times 3 gives me 0. So I did for the entire row, and I got negative 2 in this position and 2 in this other position. Now, so I'm done with this column. I come to this second row where I have this negative 1 as the leading one. As I've done it from the very beginning, I want my leading element to be positive 1. So to get positive 1 here, what I did, I multiplied the entire row by negative 1. So entire row 2 by negative 1. That gives me positives, and you can say positive 1, positive 1, positive 1, positive 1, positive 1. The other rows, I leave them the way they are. Now I want to use this leading one to create a 0 in this position. The rest I already have zeros, so I have no problem with these two. I only need a 0 in this position. And you can see, for me to achieve this, I need row 3 minus row 2. Row 3 minus row 2. So this, the entire row minus the entire row. So 1 minus 1 gives me 0. Negative 3 minus 1 gives me negative 4. Negative 1 minus 1 gives me negative 2. And negative 5 minus 1 gives me negative 6. Negative 4 minus 1 gives me negative 5. So I'm done with that. I'm done with that row. Now, you can see that my leading element is now this one. In this row is now this. So I also make this leading element to be 1. So to make it 1, I divide the entire row by negative 4. So divide row 3 by negative 4. So when that happens, this becomes 1, this becomes a half, this becomes 3 over 2, and this becomes 5 over 4. And that's what we are seeing. That's what we are seeing here. So let me just now look at what I did. So I have this row now with the leading one here. I need to use this to create zeros below it. But fortunately, I already have zeros below it. So the next thing I want is a leading one in this row, a leading element in this row, and we already have it. We already have it as 1. And below it, you have elements which are not 0. So we use this one to create a 0 in this position. So for me to do that, I need to take, it is row 5 plus 2 row 4. Now this is row 5, 1, 2, 3, 4. Yeah, row 5 plus 2 row 4. So this negative 2 plus 2 times 1 gives me 0. And this 2 plus 2 multiplied by negative 1 gives me 0. So this matrix is in a row echelon form. This matrix here is in a row echelon form as we wanted. Because we only wanted to to reduce it to row echelon form, and that is what we have done.
Welcome back. In the next video, we look at how to solve by Gaussian elimination.
Welcome to my channel, where we're looking at how to solve system of linear equations by Gaussian elimination. In our other video, we looked at reducing a matrix to echelon form, and so we'll be using that knowledge of reducing a matrix to echelon form to try and solve the system of linear equations by Gaussian elimination. So what is the procedure of how to solve a system by Gaussian elimination? So if you're given a system and you're asked to solve it by Gaussian elimination, the first thing you're supposed to do is to extract augmented matrix from that system. So extract the augmented matrix from that system of linear equations, and then after extracting the augmented matrix, reduce that augmented matrix to echelon form, and then solve by back substitution to get the solutions to the system. So I want to look at examples on how to solve a system by Gaussian elimination. So the first example is use Gaussian elimination to solve this system. So we are given 3a plus b minus c is equals to 1, a plus 4b minus 3c is 11, negative 2a plus 3b plus 5c is 21. So the first thing we do is to extract the augmented matrix. These coefficients, use this coefficient to form the matrix. So I can see 3, 2, negative 1. 3, 2, negative 1 is equals to 1. So instead of that, we just put this, and then the 1 is there. This vertical line, and then the 1 is there. Then I can see the coefficient here, 1, 4, negative 3. 1, 4, negative 3, and then 11. Then the coefficient here can see negative 2, 3, and 5. So negative 2, 3, and 5, then 11. This matrix is what I call the augmented matrix. The augmented matrix. So this is the augmented matrix. Now, with this matrix, we reduce this matrix to echelon form. So we have this leading entry here. We use this leading entry to create zeros below it in the column, first column. So to get a zero in this position, I take row 2. I take row 2 minus a third of row 1. So this will give me the new row 2. Then I also need a 0 in this position. So I'll take row 3 minus or plus 2 out of 3 of row 1. So this will give me the new row 3. So just as we did while we were looking at reducing matrices to echelon form, once you have this leading entry here, you use it to create zeros in the positions below it. So these elementary row operations give us that zero, those zeros. So let's just do it for row 2. 1 minus a third of 3. That gives me 0. And then 4 minus a third of 2 minus a third of 2. This is like 2 over 3. So it is 4 minus 2 over 3. And that gave me 10 over 3. And then negative 3 minus a third of -1. And this is like -3 plus a third. What the LCM is 3. And this will be -9 plus 1. It's -8/3. That's what I have. I do the same for this. 11 minus a third of 1. And that gave me 32/3. And then I come to this position and create a 0 here. And I've said to create a 0 here, I would have the entire row 3 plus 2/3 row 1. So in other words, -2 plus 2/3 of 3. That gives me 0 in this position. That gives me a 0 in that position. Now what about in this position? I have 3 plus 2/3 of 2. This is the same as 3 plus 4/3. Why the LCM is 3. And this will be 9 plus 4, which gives me 13/3. And that is why you're seeing this 13/3. What about in this position? I would have 5 plus 2/3 of -1. The LCM there is 3, and this will be 15 minus 2. And this is 13/3. I do the same for this position, and I get 65/3. Now, so I have this, I'm done with this first column. I now come to this second row, and I can see that my leading entry is this. So I want to use this leading entry to create a 0 in this position. How do I achieve that? To get a 0 in this position, I need, that position is in row 3. So I need this row 3 minus 13 out of 10 of row 2. 13 out of 10 of row 2. So what I mean is, this 13 out of 3, I will subtract from it 13 out of 10 of 10/3 of 10/3. And this is 13 out of 3 minus 13 out of 3, which gives me 0. And then in this position, I have 13/3 minus 13 out of 10 of -8/3. Remember, the negative and negative would be positive. So what I would then have, 2 go here 5 times, and 2 go here 4 times. So the LCM there will be 15. And through going to 15 5 times, 5 times that will be 65. And minus plus, and this is 52. This is 52. So this will give me 117 out of 15. Now, so what I did this time, I did not simplify, but if I simplify this, you'll get 117, because 2 go here 1, and then is it 117? Yes, it's supposed to be 117. So 2 go here 1 into 3 1, and then 7. So it's 117 out of 15. Doing the same from this position, you would still get again 117 out of 15. But since I had not simplified it, let me just leave them the way I had used them. They were 234 out of 30, 234 out of 30. But we've seen what we've done, that we want to use this leading one to create zeros below it. Then we shall have another leading one in this position, use it to create a zero below it. And once that is done, the matrix is in echelon form. So we have our matrix in echelon form here. Is that. This is our matrix in echelon form. Now, so we use it now to solve the system. And we write what we understand, the equations from that coming from the last matrix there. And the equations coming from the last matrix, remember it was A, B, C. So this was 3A, 2B minus C, and that's all you see. 3A plus 2B minus C equals to 1. This was the position of A. So what we have here is 10 over 3B minus 8 over 3C is equals to 2 over 3, and that's what we see here. And finally, this was A, B. So what I have here is 234 over 30. C is equals to 234 over 30. So now we solve from this bottom part going up. Solving here, multiplying both sides by the reciprocal of 234 over 30 gives me C to be 1. So I find that C is 1. Then I move this other equation and substitute 1 wherever is C. What I would have would be 10 over 3B minus 8 over 3, remember C is 1, equals to 32 over 3. In other words, 10 over 3B equals, I take this other side, I would have 40 over 3. 40 over 3. Then multiply both sides by 3 over 10. That gives me B is equals to 40 over 3 times 3 over 10. And that means B would be 4. Now, so I have the value of C and I also have the value of B. I proceed this other equation and substitute there B as 4 and substitute C as 1. Then make A the subject of the formula. A would be -2. Once I have my solutions, I have the value of C, A, C, and B. I write them in vector form, and that becomes the solution to the system. I write them in vector form. So I've written them in columns. So you may also want to write them in a row. You may want to write them as this, and there will be no problem. That will still be a solution to the system. So I want us to look at another example, how to solve a system of linear equations by Gaussian elimination. I have this system here. This is my system, and I want to solve it. So the first process, what we said, we extract the augmented matrix. So 2, -3, 1, 2, -3, 1, then 2, then 3, -4, 3, 7, 3, -4, 3, 7, then 2, 3, 2, 8, 2, 3, 2, 8, and reduce this matrix to echelon form. So we have this leading one, use it to create zeros below it. So what are our row operations? I would have row 2 minus 3 over 2 of row 1. That will give me a 0 in this position. And then in this position, I'll just take row 3 minus row 1. So let's cut out those row operations and see what we get. So 3 minus 3 over 2 of 2 gives me 0. Negative 4 minus 3 over 2 of negative 3. This will be positive. So I'm talking of negative 4 plus 9. This is 2. 9 over 2. Where the LCM is 2, and this will be negative 8 plus 9, giving us a half. And you can see the half there. That's how I got it. And then I have this 3 minus 3 over out of 2 of 1. And see, this will give us 6 minus 3 out of 2, which will be 3 out of 2. Doing the same to these two elements gives me 4 here. I now want a 0 in this position, and I said I would take row 3 minus row 1. So 2 minus 2 is 0. 3 minus 3 is 6. 2 minus 1 is 1. And 8 minus 2 is 6. Now I have this leading element here. I use it to create a 0 in this position. So what am I to do? For me to get a 0 in this position, if I was to use this element, then it will mean that I will take row 3 minus 12 of row 2. 12 of row 2. So what is 12 of 0? It will be 0. From this, I have a 0. 12 of a half is 6. From this 6, I have 0. 12 of 3 over 2 will be 18. 18 from this 1, I have negative 17. And then finally, 12 of 4 is 48. 48 from 6, I have negative 42. The matrix is in echelon form. The matrix is in echelon form. Now, since it's in echelon form, we now extract the equations from this last matrix and use those equations to solve by back substitution. So let's come up with the equations from the last matrix. And these are the equations I was able to extract. This is 2x minus 3y plus z equals to 2. That is our equation. These are half of y plus 3 over 2z is 4. And finally, negative 17z equals to negative 42. Now, so solving from the bottom going up, this last equation tells us that z is 42 over 17. Z is 42 over 17. Proceed with this other equation, and what we have is a half y equals to 4 minus 3 over 2z. But z is 42 over 17. So doing this gives us y as 10 over 17. Y becomes 10 over 17. And then you proceed this first equation, make x the subject, and substitute in the value of y and the value of z, and you get x to be 11 over 17. So we've solved that system that was given to us. Let's look at another example. And we are still using Gaussian elimination. So we have this system of linear equations, very fast, we extract the augmented matrix. And you can see in this position you have no value of x, so I make it 0. But the rest are there. They are the coefficients of these unknowns. I have 1, 2, -1, -3. 1, 2, -1, -3. Then 0, 2, -2, 1. 0, 2, -2, 1. Then 1, -1, 2, 3. 1, -1, 2, 3. Very first, we reduce this matrix to echelon form. And so far, you know how to reduce these matrices to echelon form. When you do that, this is what you finally arrive at. This is the final matrix in echelon form. So this is an echelon form. Now, so we write what we understand by these equations, and I understand that since it was x, y, z, this would be 2, now x plus 2y minus z is -3, and this would be 2y minus 2z would be 1, and this would be 0, x plus 0, y plus 0, z is 7.5. It's this last equation that interests me, that x are that we can get values for x, y, and z such that when multiplied by 0, they give us an non-zero element or a non-zero number. This is not possible. It's not possible that we can have 0 times a number plus 0 times a number plus 0 times another number and the result be non-zero. It's not possible. And so since that is impossible, it means this system that we were given, the system that we were given above to solve, has no solution. And so that's why I wrote and said the last row of the last part implies 0x plus 0y plus 0z is 7.5, which is not possible. And therefore, the system that we were given has no solution. Or we can say the system is inconsistent. Inconsistent. This term we looked at it earlier when we began looking at solution of systems of linear equation. So far we've looked at an example where the system had a solution and an example where the system has no solution. So let's look at this other example and see whether the system has a solution or solutions or no solution. This is our system. So very first, we extract the augmented matrix, and this is the augmented matrix that I extracted out of our system. This is the augmented matrix. I want to very fast skip the other steps because you know to reduce to echelon form. We're just reducing this matrix to echelon form. This is the augmented matrix. And when I did that, this is what I got as my final result. So do it and see that you get that. I'm interested with this last row here. Look what the other two examples we looked at before we come to that. Look at this example. In this example, this was our last row. And it was very easy to see that -17z equal -42. That means the value of z could be obtained very fast. And therefore, the other values would also be obtained by back substitution. Then we came to this other example. And look at how the last row was. that we had 0 plus 0 plus 0, giving us a non-zero element. And we concluded and said that that is not possible, and therefore this system lacks solutions. Now let's come to our current example. And our current example, after reducing the system to echelon form, this is what we get. This is the echelon matrix. And look at the last row. Once I see the last row as 0, 0, 0 equals to 0, what this tells me is that this system has solutions. Not one solution, but it has infinitely many solutions. Because I have 0 plus 0 plus 0 plus 0 is equals to 0. So there are infinitely many solutions. Now, so how do we solve this? First thing, we extract what are the equations. Like I can see here, I have x minus 3y plus z equals to 2. And I have y plus 4z is 3. You can see that the leading element here is x, and the leading element here is y. And that z is not leading, is not a leading element. So the element that is not leading, we call it a free element or free variable. So in this case, z is a free variable. X and y are leading elements. Z is not, and therefore z is a free variable. So what we do in this case is that we solve the leading elements in terms of the free variables. We solve for the leading elements in terms of the free variables. And we can equate the free variables to some parameter, let me say t or s, where these ones represent any number, where t and s represent any number. So I've said that once I look at this shows that the above system has infinitely many solutions. So to solve this, we write the variables corresponding to the leading entries. The leading variables, in this case x and y, in terms of the other variables. And the other variables that are not leading, we call them the free variables. So in this solution, the leading variables are x and y, while z is a free variable. So what it means is that x should be solved in terms of z, and y should also be solved in terms of z. So I've said that we assign parameters to free variables. For example, we can let z be t, where t here will be 1, will be 2, 3, 4, and so on, or negative 10, and so on. Is there any number? And solve from the bottom going up. And so when you solve from the bottom going up, what we have, supposing that z is t. If z is t, what I would then have, this would mean that I have y is equals to 3z is equals to 3 minus 4z, but z is t. Just a minute. But z is t, so y is 3 minus 4t. I can also solve x. From here, I can see that x equals 2 minus z minus plus 3y. 2 minus z plus 3y. But I know what z is, and I know what this is 2. So this is the same as 2 minus z. Z is t plus 3y. But y is 3 minus 40. What does this give us? This is 2 minus t, but this is 9. plus 9, and this is negative 12t. Negative 12t. This is plus. So what I have, this is 9 plus 2, which is 11. Which is 11. And then negative t, negative 12t will give us negative 13t. So that becomes our x. And that's what I have. That's what I have. Just a slight correction that this is z. Z was t. Y was 3 minus 4t. And x was 11 minus 13t. So this is our solution. Remember that this system has various solutions. If you make t to be 1, you get one set of solutions. If you make t the bottom of that matrix in echelon form, this was the bottom of the matrix in echelon form. I want to look at one more example, and this is the example. Use Gaussian elimination, or using Gaussian elimination, find the general solution to the system below. Like the example we've had above, what we wrote was the general solution. And that's, I said that if t is 1, then we would have one set of solutions. If t is 2, we'd have another set. So what we came up with was a general solution. So again, we require general solution from this. When we see, let's just extract the augmented matrix and then reduce to echelon form. When I did that, this was the augmented matrix, and then this was the echelon form of base. And then now extracting this is x1 plus 2x2 plus 3x3 plus x4 plus 2x5 plus 2x6 is equals to that. And that's what I have. And then I do the same for this to come up with this equation, the same to this, or this equation. Then lastly, I have this this is x5 minus x6 is equals to 4. But what is interesting is the last row telling me that this system has infinitely many solutions. Is what it's telling me. And once I see this, I know that I'll be solving the leading variables in terms of the free variables. I'll be solving the leading variables in terms of the free variables. And I've said that in this example, I can see that x1, x2, x3, and x5 are leading variables, while x4 and x6 are free variables. So I'll assign the free variables parameters. So that's what I did. I assigned x4 to be s and x6 to be t. And so I began solving. So if you begin from this solving, x5 will be 4 minus plus x6, but x6 is t. So that's why you see that I say x5 is 4 plus t. 4 plus t is x5. But x6 is t. x6 is t. So x5 is that. x4 is s. What about x3? So just move here and make x3 the subject of the formula. So x3 is negative 1 minus 5 over 4 x6 which is 2 plus, no, it's minus 3 over 2 x5, which we now have. X5 was 4 minus plus 2, that was x5. Then minus a half of x4. x4 is s. Doing that gives me, I did that and I found that x3 was -7 minus half s minus 11 over 40. I moved up and made x2 the subject. Because I already have x3, I have x4, I have x5, I have x6 equals to 0. Substitute x3, substitute x4, substitute x5, and substitute x6, and make x2 the subject. Doing that left me with x2 as 3 minus half s plus 3/4 t. Then I moved to the first equation and made x1 the subject. And remember that I've already found these other values. Substitute them here and make x1 the subject. And doing that gave me 9 plus 3s over 2 plus 11t over 4 as x1. And that is how we solve a system of linear equations by Gaussian elimination.
In what follows, we learn how to transform matrices to reduced row echelon form.
Welcome to my channel, and let's look at reduced row echelon form of matrices. We had looked at row echelon form of matrices earlier, row echelon form of matrices. Now this time I want to look at reduced row echelon form. This is also known as reduced echelon matrix, reduced echelon form. So you can call it reduced row echelon form or reduced echelon form. That's what we want to look at. And so what we'll look at first is, when do we say that a matrix is in a reduced row echelon form? So a matrix is said to be in a reduced row echelon form, or precisely as being in reduced echelon form, if it fulfills the following properties. That 1, it must be in row echelon form. And 2, the leading entry in every non-zero row must be a 1, which we shall call the leading one. So the leading element in every non-zero row must be a 1. And then that leading one must be the only non-zero element in its column. That leading one must be the only non-zero element or entry in its column. So that way, then we say that the matrix, if it fulfills these conditions, we say it is in reduced echelon form or in reduced row echelon form. So let's look at example of matrices that are in reduced row echelon form. So the first example is this, and I'm just going through the entries, through the properties. The first property is that every non-zero row has 1 as the leading element. So I have this non-zero row. Its leading element or entry is 1. This non-zero row, its leading entry is 1. And this row also has 1 as the leading entry. And notice that this 1 is the only non-zero element in its column. This 1 is also the only non-zero element in its column. And this 1 is also the only non-zero element in its column. The same thing can be observed here. The leading entry in this row is 1. The leading entry in this row is 1. The leading entry in this row is 1. And a row of zeros must be at the bottom. Notice that this 1 is the only non-zero element or entry in this column. The same to this 1 and the same to this 1. So these two matrices are in reduced row echelon form. And these two are also in reduced row echelon form. Because you can see the leading one is here. There's a leading one here, there's a leading one here, there's a leading one here. And these leading ones are the only non-zero elements or entries in their column. And the same applies to this matrix. So this matrix is also in a reduced row echelon form. So that's basically what we'll be trying to achieve, what we will be wanting to achieve every time we are told to reduce the matrix to reduced row echelon form. So let's look at this example. The example says that transform the following matrix to reduced row echelon form. Transform the matrix to reduced row echelon form. Somebody else will have said that transform the matrix to reduced echelon form without the word row. So again, it will still mean the same thing. It will still mean the same thing. Now, so to do that, we look at this matrix and you can see that this first row here is non-zero row. The leading element here is 2. So we make it 1. So we make it 1 by dividing row 1 by 2. So divide row 1 by 2. Because the leading element must be 1. So when I do that, I get 1, a half, and negative 1. So I have achieved what I wanted. I wanted that the leading element should be 1, and I have it. Once I have this leading element as 1, I want it to be the only non-zero entry in this column. So I use it to create a 0 in this position and a 0 in this position. So how do I get a 0 in this position? By taking row 2 and subtracting 3 row 1. Remember, I'm using this leading entry there. I'm using that leading entry. And as I said, whenever you do this, it's always good to show us your elementary row operations. For instance, I've shown my row operation that gives me this matrix. And I'm now showing the operation that will give us this other matrix. So to get a 0 in this position, row 2 minus 3, row 1. What about in this position? Get a 0 there. I will take row 3 minus row 1. So let's do that very fast. 3 minus 3 times 1. This is 0. Negative 3 minus 3 multiplied by half is the same as the same there is 2. And this would be negative 6, negative 3, which is negative 9 out of 2. What about here? Negative 1 minus 3 multiplied by negative 1. Remember, these minuses multiplied will be positive. So I'll have negative 1 plus 4. No, negative 1 plus 3, which is 2. Now, for these other rows, just subtract row 3 minus row 1. So 1 minus 1 is 0. Negative 2 minus a half will be negative 5 over 2. And then 3 minus negative 1 will give me 4. I'm done with this first column. Now I come to this leading entry here. Make it 1. How do I make it 1? By multiplying row 2 times negative 2 over 9. So the entire row 2 multiplied by negative 2 over 9. That gives me 1 here and negative 4 over 9 here. So the other rows, I've left them the way they are. I've only changed this row because I wanted this one to be 1. Once I have this 1, I want it to be the only non-zero element in row 2, in column 2. I want it to be the only non-zero element in column 2. So I want to use it to make a 0 in this position and then a 0 in this position. How do I get a 0 in this position? I get that by taking row 1. And remember, I'm using this leading element. Every time you create a leading element, use it to create zeros elsewhere in the column. So row 1 minus a half of row 2. And to get a 0 in this position, I take row 3 plus 5 out of 2 of row 2. Let's do that. So row 1 minus a half of 1 gives me 0. And then negative 1 minus a half of negative 4 over 9. This is the same as negative 1 plus 4. Let me just say 2 goes here twice. So that I have this should be 2 out of 9. And this is negative. It gives me, what is that? Just a minute. Let me erase this so that it's clear. I want to get a 0 in this position. I've said I multiply this by half and subtract from this. So if I multiply this by half, and subtract from this a half, I'll have a 0. And do the same for this. Negative 1 minus a half of negative 4 over 9. And this will be 2 then. So I would have negative 1 plus 2 over 9, which is negative 7 over 9. So this is not correct here. It's supposed to be negative 7. Negative 7 over 9. Not negative 1. It's supposed to be negative 7 over 9. Negative 7 over 9. This, what about, we are done with the first row. Now we come to the second row and create a 0 in this position. And we already said that will be achieved when we take row 3, and then into it add 5 out of 2 of row 2. 5 over 2 of row 2. So let's just do that, because I'm seeing that the first working that I have here is not correct. So let's just work out, and hope you can follow, and then do it later to find out the correct one, because supposing I'm doing something that's not correct, but the procedure is correct. Now, so row 3 is negative 5 over 2, then plus 5 over 2 of 1. And this gives me 0. This 0. What about here? 4 plus 5 over 2 of this, of negative 4 over 9. This will go here twice. So what I'd be having before minus 10 out of 9, which is same as 36 minus 10. That's 26 over 9. And that is this 26 over 9. Then the next thing I want is to create a 1 in this position. That's the next thing I want. You just erase this. There's this. And you know that we corrected this entry and wrote it as negative 7 over 9. Now we have this, make it 1 by multiplying this row. Multiply this row by 9 over 26. So row 3 by 9 over 26. That gives me 1 here. And this remains to be negative 4 over 9. And this is what we changed it to be negative 7 over 9. Now I want this 1 to be the only non-zero element in this column. On this 1 here, it's 1 of negative 1. It's 1. So I want that 1 to be the only non-zero entry in this column. So what do I want? I want to multiply the entire row 3. So because I want a 0 in this position, so I would have row 2 plus 4 over 9 of row 3. And then row 1 plus 7 over 9 of row 3. So that will give me a 0 here and another 0 here. So that our final matrix in reduced echelon form would be this. That would be the first final matrix that we say is in a reduced row echelon form. Let's look at another example. An example is transform this matrix to reduced echelon form. And so very fast, now that we know the procedure, we want this 1, this is leading 1. Unfortunately, it's already a 1. If it would have been something different, we would have created a 1 in this position. But since it's already a 1, we ensure that this becomes 0 and this becomes 0. So how do we do that? By taking row 2 plus row 1, gives me a 0 in this position, and then row 3 minus 5 row 1 gives me a 0 in this position, in this other position. So let's do that. This plus this gives me 0. This plus this gives me negative 1. This plus this gives me negative 4. And then row 3 minus 5 row 1, this 5 minus 5 times 1 gives me 0. And this negative 13 minus 5 minus 3, this will be 15. This 15 added to negative 13 gives me 2. And then the same, we do the same for this and that to get an 8, to get 8 in this position. Now, so we have this matrix. I want this element to be 1. So I multiply row 2 by negative 1. So when I multiply row 2 by negative 1 and leave the other rows the way they are, this becomes positive 1, this becomes positive 4. I have a 1 in the position I wanted. I use it to get a 0 in this position. So to get a 0 in this position, I would have row 3 minus 2 row 2. Row 3 minus 2 row 2. So when I do that, I get a zeros in the last row. And elsewhere I have this. The matrix that we now have, this matrix, is in a reduced row echelon form. This matrix in a reduced row echelon form, or in a reduced echelon form as it was required. Let's do one more example. And the example here is apply elementary row operations to transform the following matrix to reduced row echelon form. Now, so what I've shown here is this. So let me just see what I did here. I have this one. I use it to get a 0 here, a 0 here, a 0 here, a 0 here. So what are my row operations? When you're doing it, ensure that you have enough space here that you can write your row operations above this up. But for me, because my space is not enough, let me write my row operations here. So to get a 0 in this position, I took row 2 minus 2 row 1. And then row 3 minus 3 row 1. And then row 4 minus row 1. And then row 5 minus 2 row 1. So when you do that, this is the matrix you get. This is the matrix you get. Now, so we'll be done with the first column. We now come to this second row, and this is our leading one. We make it 1 by multiplying row 2 by negative 1. Multiplying row 2 by negative 1. And so when that happens, and the other rows are left the way they are, what we get will be this. That's what I get. So you can see now, I multiply row 2 by negative 1, and I have this. The other rows, I leave them the way they are. Now, so what next is to use this one that we created to have zeros elsewhere in the column below it. So the most fortunate thing is that we already have a 0 here and another one here. So we're only left with creating a 0 in this position. So to create a 0 in this position, we need row 3 minus row 2. Row 3 minus row 2. So when I take this minus that, I have a 0. This minus that, I have a negative 4. This minus that, I have a negative 2, and so on. So this is now our leading element. We must make it leading 1 by dividing row 3 by negative 4. So when you divide row 3 by negative 4, you'd have 1, a half, 3 out of 2, and then 5 out of 4. So we obtain this matrix. Now, so then the other leading element that we now have on this matrix will be this. And we use it to create zeros elsewhere. It's fortunate that it's already a 1. Otherwise, we would have created it to be 1. Since it's already a 1, we multiply row 2. No, which row is that? 1, 2, 3, 4. Row 4 by 2. Row 4 by 2 and add to row 5 to get a 0 in this position. So row 5 plus 2 row 4 gives us a 0 here. It seems like I repeated these two matrices by just the same. These are repetition. Or maybe there was a negative sign and so I had to remove it. But it's okay because I'm seeing this matrix is a repetition of this. But you go through slowly and see what happened. Now, so when I take what I've just said, because I've said that I would take row 5 plus 2 row 4. When that happens, this element becomes 0 and this also becomes 0. And so we have this matrix in reduced echelon form as required, because we wanted to write that matrix in reduced echelon form. And that is what we've just done. So you go through those workings slowly and see that you get the same results, or if there's a mistake, you can try and rectify. But the procedure is what I've shown you. Thank you.
Let us now learn how to solve systems of linear equation by Gauss-Jordan elimination.
Welcome to my channel. Today we look at another method of solving a system of linear equations, and this is the Gauss-Jordan elimination method. Now, lastly, in the previous video we looked at transforming a matrix to reduced row echelon form, and that knowledge will be very much useful to us today. So how do we solve a system by Gauss-Jordan elimination? So to solve a system by Gauss-Jordan elimination, the first thing you do is you extract the augmented matrix from the given system and then transform that augmented matrix to reduced row echelon form. Then by use of back substitution, solve the system. So those are the three steps that I've written. That we extract the augmented matrix from the system, then transform that augmented matrix to reduce the row echelon form, and then use back substitution to solve the system. So let's just put this in practice by looking at one example. So the example that I want us to look at is this, and the question is use Gauss-Jordan elimination to solve this system. So the first thing we do, we extract the augmented matrix. I can see 3, 2, negative 1, then 1, 3, 2, negative 1, then 1, 1, 4, negative 3, 11, and then 2, no, negative 2, 3, 5, 21. Now, I've extracted the augmented matrix. This is the augmented matrix. This one here is our augmented matrix. Now, with this augmented matrix, what we were supposed to do is to transform it to reduced echelon form. Transform it to reduced echelon form or reduced row echelon form. And then after transforming, we shall now use back substitution to solve the system. So we already know how to transform matrix to reduced echelon form, but I'll repeat the steps here so that in our next example we will move faster. So to transform this matrix to reduced row echelon form, the first thing we must put in our mind is that every leading element must be a 1. So this leading element here, we make it 1. How do we do that? By taking row 1 and then dividing by 3. So if I divide row 1 by 3, I would have 1 here, 2 over 3, negative a third, then a third. So that gives me this matrix. And remember, we said that whenever you are doing this type of question, write the row operation that you are carrying out. So my row operation is here. Now, I now have this matrix. I have this created leading one. I use it. Remember that this leading one must be the only non-zero entry in its column. So use it to create a 0 here and a 0 here. How do I get a 0 here? By minus row 1. How do I get a 0 here? By taking row 3 plus 2 row 1. I'm using this element. So this is easy. Row 2 minus row 1 gives me this. Is 1 minus 1 will be 0. 4 minus 2/3 will give me 10 over 3. Negative 3 minus a third. That is negative 3 plus a third will give me negative 8 over 3. So I do the same until I get 32 over 3. Now let me come to this third row. Row 3 plus 2 row 1. So negative 2 plus 2 multiplied by 1. This one gives me 0. 3 plus 2 multiplied by this, 4 over 3. This is 13 over 3. I do the same for the entire row, and I get this matrix. Now, I have this leading element here, want it to be 1. So that means row 2 times 3 over 10 times 3 over 10 gives me this matrix with a 1 here. Can you say 1 is there? That's what I wanted. I have this leading one. I use it to create a 0 in this position. Get a 0 in this position. So to create a 0 in this position, that position is in row 3. So row 3 minus 13 over 3 of row 2. This minus 13 over 3 of this gives me 0. And then 13 over 3 here minus 13 over 3 of -4 over 5. And what you notice is that this will be positive. This will be positive. And the LCM will be 15. So this will go there into 15 5 times. 5 times this will be 65. And this was 4. 4 times 13 will be 52. So this is 117 over 15 that I have here. Doing the same gives me this 117 over 15. So I'm done with this, and I'm also done with this. Remember, I was using this one. Where was that? I used this one to get a 0. So how did we do that? Let me just repeat what I did here, because I wanted a 0 in this position, and then I wanted a 0 in this position. So for me to get a 0 in this position, I took row 1 minus 2 over 3 of row 2. Then to get a 0 in this position, I took row 3 minus 13 over 3 of row 2. And that is what gave me this matrix. That's what gave me this matrix. With a 0 in this position, then a 0 in this position. Now, so I'm done with this column and this column. I come this row, and I can see that this is the lead element, and that it's not 1. So to make it 1, I have to multiply row 3 by 15 over 107. So when you do that, you have a 1 here. You have a 1 in this position. So this one times 15 over 107. This one times 15 over 107. I have a 1 and a 1. Now that I have this one, I use it to create a 0 here and another 0 here. How do I create a 0 in row 1? I will have to take row 1 minus 3 over 15, row 3. And I would have to take row 2 plus 4 over 5, row 3. That gives me 0 and 0 in that position. And so I have my matrix transformed to reduced row echelon form. So now, how do I get the solutions? I can see that this was A, B, C, A, B, C, A, B, C. So that means A is -2, B is 4, and C is 1. So when we solve, and it's always good to solve from the bottom, because in some cases, it will not be this easy to see. So C is 1, B is 4, and C is -2. So we can write our solution this way. We can write our solution that way. So let's look at the next example. And we are still using Gauss-Jordan elimination. And so this time will not take a lot of time trying to reduce the matrix to reduced echelon form, because we already know how to do that. So the system given to us is this. We extract the augmented matrix, and this is our augmented matrix. This is the augmented matrix. We already have a 1 in this position, so we use it to create zeros elsewhere in the column. In other words, we have row 2 plus row 1 will give us 0 here. So let's just do that. This will be 0, this will be -1, this will be -4, and this will be -3. And that's what I have in this row. And then row 3 minus 5, row 1. Row 3 minus 5, row 1. So this minus 5 of this will be 0. -13 minus 5 of -3, the same as -13 plus 15, which will be 3. And then 13 minus 5 of 1 will be 8. And then 16 minus 5 of 2 would be 6. That's what we have. So we now have to make this element be positive 1, because the leading element must be 1 in for us to transform a matrix to reduced echelon form. The leading element must be 1. So for us to have a 1 in this position, 1 row 2 times -1. So if I multiply this by -1, now +1, +4, +3 here. Now this leading element here should be used to create a 0 here, another 0 here. How do we get a 0 here? We would get a 0 there by taking row 1 plus 3 row 2. So row 1 plus 3 row 2. So this is 1 plus 3 multiplied by 0 would be 1. This 1 plus this -3 plus 3 multiplied by 1 would be 0. And then this 1 plus 3 multiplied by 4 would be 13. This 2 plus 3 multiplied by 3 would be 11. And how do I get a 0 here? By taking row 3 minus 2 row 2. Row 3 minus 3 minus 2 row 2. So this 2 minus 2 row 1 row 2, element in row 2, that gives me 0. This 8 minus 2 multiplied by 4 gives me 0. And the same 6 be 0. So you have this final matrix. This final matrix is in the reduced row echelon form as we required. So we are supposed to solve, and you see, when we were looking at Gaussian elimination, we said that whenever we have zeros equals to 0, then that system of linear equations would have infinitely many solutions. Would have infinitely many solutions. So there is that x. See, this was value of x, this was the value of y, and this was the value of z. So I'm saying x plus 13z is 11. X plus 13z is 11. I'm also saying this was x, so this is y plus 4z is 3. Y plus 4z is 3. Remember the leading variables here, x and y. X and y are leading variables, while z is a free variable. So whenever we have this, then the free variables are assigned parameters. And then the leading variables are solved in terms of the free variables. The leading variables are solved in terms of the free variables. So that means we should solve x in terms of z and y in terms of z, and then we assign z a parameter, where parameter is any number. So I've said this shows that the above system has infinitely many solutions. To solve this, we write the variables corresponding to the leading entries in terms of other variables, in terms of the free variables. So let's assign z, which is a free variable. Let's assign it t. So t here is any number. T could be 2, could be 10, could be -3, and so on. So if z is t, what is y? Go back to the equation and make y the subject. Y would be 3 minus 4t. What about x? X would be 11 minus 13t. And then we just need to write our solution as a vector. X, just a small correction here. This was z. This was z. So x, if z was t, y was 3 minus 4t, and x was 11 minus 3t. Let's look at another example, and we are still using Gauss-Jordan elimination. We are given this system, and we are told, using Gauss-Jordan elimination, find the general solution to the system, and this is a system. So the first thing we do is to extract the augmented matrix. And when I did that, this was the augmented matrix. And then transform it to reduced row echelon form, and that's what I got. This is what we get. So just try at your own time to transform this as exercise. Transform this matrix to reduced echelon form and see that it appears as your final matrix. Once you have this final matrix, which ones are your leading entries? From what I see, and you must be seeing the same, this is a leading entry, this is another one, this is another one, this is another one. So x1 is a leading variable, and you can see x2 is another leading variable, x3 is a leading variable, this was x4, x5 is a leading variable. So the leading variables are x1, x2, x3, and x5. They have to be solved in terms of the free variables. The free variables are x4 and x6. So what I did was I just extracted, this was x1, x2, x3, negative x1, negative 3 over 2 x4, this was x5, negative 11 over 4 x6 is equals to 9. Then here, this was x2, x4, x6. So I have x2 plus a half x4 minus 3 over 4 x6 is equals to 3. I do the same for this. This is x3 plus a half x4 plus 11 over 4 x6. Then finally, this is x5 minus x6. And that gives me these equations. Now with these equations, I can see the leading variables and I can see the free variables. The free variables are the ones which are not leading. So x4 is free, x6 is also free. So I assign them parameters. I say, for example, let x4 be s and x6 be t. and then solve the rest. X5 is 4 plus X6. Make it the subject. X5 would be 4 plus X6, but X6 is T. So this is X5. X4 is this, is S. Again, come to this X3, make it the subject. X3 is -7 minus 11 over 4 T minus a half S. And that's what I have. That's what I have. Because this is a half S. And this is 11 over 4 T. What about X2? Make it the subject. It will be 3 plus 3 over 4 T minus a half S. That's what I have. And again, make this one the subject. Then after you've done that, write your solution as a vector. Write your solution as a vector. And so this is what I have. This is my solution. So and remember, this solution, you can have it, I've decided to have it in decimals. You can also have it in fractions. And I've also decided to have it as a column vector. You may want to have it in a row form. That's how we'll solve by Gauss-Jordan elimination.
Thank you for watching. We've exhausted our subtopics for today. Remember to subscribe if you're not subscribed, so that next time I load a video, you can automatically see it. Thank you.